Have you ever wondered how your calculator comes up with decimal approximations for irrational numbers, trig functions, or logarithms? Do you think there's some little magical creature inside the box of your calculator measuring little right triangles with little bitty rulers, getting the ratio of the opposite side over the hypotenuse of a triangle to find sine? Not really, no. I'm sure you didn't think that. But maybe it never occurred to you how a number that is geometric in nature could be approximated on your calculator. Where are those magic decimal places coming from? Well, it's because of power series. A power series is an infinite series of power functions. In other words, a polynomial, actually, an infinite polynomial with infinitely many terms, functions of the form ax to the b, which are raised to increasingly higher powers. A special group of converging power series called Taylor series, I'm not joking, I didn't make them up, but that is their name, is used to approximate transcendental numbers such as e, cosine x, and sine x that cannot be calculated using algebraic operations. Logarithms are also transcendental numbers, for example. So let's take a look at e. E to the x equals, and we got this crazy sigma notation here, and we have this explanation mark, which doesn't mean n like I'm excited about n, it means something different. When you see n factorial, for example, I'll just write it up kind of at the top where I have a little space. If you see 5 factorial, it means 5 times 4 times 3 times 2 times 1. So you start whatever that number is, and you count down to 1, multiplying them together. So 5 factorial turns out to be 120. Also, just to recall, 0 factorial is equal to 1, not 0. 1 factorial is also equal to 1. 2 factorial is equal to 2, because it's 2 times 1. 3 factorial is equal to 3 times 2 times 1, which is 6, etc. Okay, so that's what a factorial is. So when we see this factorial, notice we have the limit, the sum, not the limit. I'm used to saying limit. The sum, as n goes from 0 to infinity, of x to the n over n factorial, and that is equal to e to the x. So, for example, if I wanted to find e to the first power, I would put 1 in for x in this sequence. If I wanted to find e to the second power, I would put 2 in for x. If I wanted to find e to the 3.5, I would put 3.5 in for x. But the n's are just counted up with each succeeding term. So let's see what this looks like if we write out the terms of these sequence. So n equals 0, n equals 1, n equals 2, n equals 3, and so forth. So if n is 0, we have x to the 0 over 0 factorial. Then we have x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Now, when x to the 0 is 1, because anything raised to the 0 power is 1, except 0 to the 0 is undefined. 0 factorial has been defined as 1 also, so the first number is just 1. X to the first is x, and x over 1 is 1, so actually this is just x. And I'm going to leave the factorial symbols in after this. This is x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 not times plus x to the 4th over 4 factorial, etc. And this goes on, this pattern continues. Now, if I were to try to estimate e using the factorial pattern, I would just, as I said, put 1 in. So I'd have 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120, plus 1 over 6 factorial, which is 7 times 6 times 5 times 4, etc. That's 720. And I just keep adding those up. And the more terms I add up, the closer the approximation gets to e. And when I add up just a few terms, I can approximate e to just maybe 1 or 2 decimal places. If I add up more terms, I can approximate e to more decimal places accurately. So let's just look at what e looks like on the calculator. So if I go to my calculator, if I push this little button that has a pi symbol, I can find e. If I just type in e, it does not give me the number e. But if I type in e and it looks bold like this, and I do a Control-Enter, I didn't do Control-Enter. If I do Control-Enter, I get 2.71828182446. So that's what E equals. So you might want to record that on your notes. Now, if I want to approximate E, and I guess we can actually go back to the notes, 2.71828. If I substitute 1 into the formula, I should be able to approximate E. So how many terms would it take to get E to 5 decimal place accuracy, to get 2.71828? So let's go ahead and try that. Actually, I want to do that on the calculator. So I start out with 1 plus, why don't we do, we'll have 1, we have 1, and then the second term is x, so that would be 1. And the third term would be 1 over 2. And the fourth term is going to be 1 divided by 6, because that's 3 factorial, plus 1 divided by 4 factorial. 6 times 4 is 24, plus 1 divided by 5 factorial would be 4 factorial. 4 times 3 times 2 times 1 times 5. So 5 times 24 is 120. So let's see what we have so far. Oops, I put an x instead of a 1. That was not supposed to happen. Let me go back and change my x to a 1. Probably somebody once again screaming half point at me, and I just can't hear you. Okay, well, I've got 2.71, so I'm to 2 decimal place accuracy. Let's add a couple of more terms. So we need to add some, we're up to 1 over 5 factorial. So let's add plus 1 over 6 factorial. Now, to get the factorial button, you'll notice a little button down here that has an exclamation point and a question mark on it. So there's our factorial symbol right here. Of course, I'm grabbing the factorial symbol before I put the 6 in. I should actually have a 6 there. Let's see what we have now. Oh, we're up to 3 decimal place accuracy now, because we're looking for 2.71828. Okay, so let's add another term. So 1 divided by 7 factorial. So get my little factorial symbol again. And I'm up to 4 decimal place accuracy. Let's see how many more terms it would take. So plus 1 divided by 8 factorial. 2.71827, almost, and looks like 1 more term will do it. Answer plus 1 divided by 9 factorial. Okay, which is actually 10 terms, because we started out with n equal to 0. So we start out with 1 divided by 0 factorial. So there we are with 10 terms at 5 decimal place accuracy. I'm going to go back and record that it took me 10 terms to get 5 decimal place accuracy. Now, E squared. Let's figure out what E squared is, first of all. So I'm going to get my E from my special menu here. E squared. And that's 7.38905. That's what I'm looking for. Now, go back up. I'm going to do this a little bit differently. I'm going to use the summation notation on the calculator. So if you push the little button to the left of the book icon, you'll see this highlighted in blue here on my calculator. There is the summation notation. So let's put in here n, and we'll tab over to 0 because we're starting with n equals 0. And when we tab up, let's see, how many terms might we want? Well, we could try 10 terms and see how well we did with 10 terms, because we used 10 terms before. Now, for x here, it's x to the n over n factorial. Well, I need my n's in there because my n is what counts up. But my x goes to whatever whatever e to the x is. That's my x. So I'm going to put 2 to the n over n factorial divided by n factorial. And when I push enter, I get this crazy fraction, because it is adding up a bunch of fractions, and you know how this Inspire loves to just keep exact numbers. So I'm going to push Control Enter, and I'm at 7.38905. not quite enough decimal places. So why don't we grab this thing and let's change the number of terms. Why don't we make it 12 and see what 12 does. I'm going to do a control enter this time. 7.38905. I think that gives me enough decimal place accuracy. Yep. So it took 12 terms this time to get 7.38905. Actually, I take that back. That's 13 terms. When you go from 0 to 12, you've done 13 terms. So it took 13 terms. It turns out the bigger that x is, so if I raise e to a higher power, it's going to take more terms to get a higher decimal place accuracy. And we're going to look at a graph to kind of see why that is. If we look at the graph here, I have on the graph, I have this red graph is the graph of e to the x, and the black graph is the graph of the first two terms of the power series that approximates e to the x, 1 plus x. The next term would be plus x squared over 2 factorial, which is x squared over 2. So let's see what happens when we add that term in. Now, notice that the graph is closer fitting to the e to the x at a certain section. So kind of like right in here, there's a little section where they're very close. So if I were picking a value like e to the first, that would give me a decent approximation. But if I were picking a value like e squared, notice that it's a lot farther off up there than it was before. So I want to get, if I add more terms, the more terms I add, let's see if I can turn that off, the more closely the e to the power series approximation will approach the graph of e to the x. So let's add another term and just see what happens. So the next one would be plus x to the third divided by 3 factorial. Let's see, x to the third divided by 3 factorial, which is 6. Okay, so notice how much more closely the graph fits to e to the x. And so the more terms we add, the farther out I can get away from the origin and still have my approximation be close to what e to the x is. Okay, let's look at the next type of power series. We also have power series for sine of x and, oops, I think I skipped a page. There we go, for sine of x and cosine of x. Now, let's go ahead and just write out what this series is going to look like. It's a little more complicated. Let's put in values for n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. Let's put a few values in here. And when we plug in n equals 0, we get negative 1 to the 0, x to the 2 times 0 plus 1. Well, that'd be x to the first. And then 2 times 0 plus 1 factorial. So that would be 1 factorial. So negative 1 to the 0, x to the first over 1 factorial. Then the next one is going to be negative 1 squared. No. Oh, that's supposed to be negative 1 to the 0. Oh, sorry. Yeah, that's right. Never mind, never mind. I did it right. I just was not thinking. This is going to be negative 1 to the first now, times x to the 2 times 1 plus 1. 2 times 1 plus 1 is third, x to the third, then this would be 3 factorial. Then we have negative 1 squared times x to the 2 times 2 plus 1, which is 5, over 5 factorial. Notice that the term 2n plus 1, or the expression 2n plus 1, always gives you an odd number, because 2n is always an even number, and then you add 1 and it's an odd number. So when you see 2n plus 1, we're just getting a series of odd numbers. And I think I'm going to run out of room to do all of these, but negative 1 cubed, and then 2n plus 1 would be x to the 7th over 7 factorial. So let's simplify this a little. The negative 1 to the 0 is just 1. X to the first is just x, and 1 factorial is just 1. So this just turns out to be x. The second term, negative 1 to the first, well, that is a negative number. So that means I'm actually subtracting. My next term is x cubed over 3 factorial, but I'm subtracting it. Then when I see negative 1 squared for the next term right here, that's positive again. So it's plus x to the 5th over 5 factorial. And then you see negative 1 cubed, so that's minus x to the 7th over 7 factorial. And I imagine you can figure out the next one would be plus x to the 9th over 9 factorial, etc., and then minus again. So that's what the sine function looks like. The cosine function is very similar. Instead of the 2n plus 1, I just have 2n, which means I'm going to get all even numbered terms for cosine. So if we plug in, and notice we also have alternating signs, so when I put the 0 power negative 1 to the 0, the first term is going to be positive, the second term will be negative, and so forth. So what I end up getting when I first get the first term is just negative 1 to the 0, which is 1, x to the 2 times 0. So I get 1 times x to the 0 over 0 factorial. That ends up just being 1. Then I end up minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. Okay, so I end up with alternating signs, only now everything is negative. Everything, all the powers are even powers, is what I meant to say. Now, let's do the same thing that we did for sine and cosine. And remember, with e to the x, it took me 10 terms to get e to the first, and it took me 13 terms to get e squared using the power series approximation. Let's try sine. I want to do sine of 0.2 on the calculator first. So I'm going to open a new calculator page, I think, here. And I'm just going to do sine of 0.2. And you have to be in radian mode, and I am in radian mode for this to work. The decimal approximation only works in radian mode. So there's sine of 0.2. Now, to do the power series approximation, every place there's an x, I'm going to put 0.2. So my first term for sine is just 0.2. Well, 0.2 by itself is not a bad approximation for 0.198. It's actually really close. So even one term is a close approximation. But let's start out with two terms. 0.2 minus 0.2 cubed divided by 3 factorial, which is 6. Look at that. 2 terms, and I'm already at 5 decimal place accuracy. Now the next one says, what about trying 2, sine of 2? So if I do sine of 2, okay, I get 0.90929. Well, let's try our little trick that we did with the sigma notation. So rather than me typing in, term after term, let's do a little shortcut here. Let's put in what we need to put in here. N, 0. I don't know. Let's start with maybe 5 terms. Let's see how 5 terms does. I don't know how 5 terms will do. And then let's put in we have to type this in. It'll take a little longer. Negative 1 to the n power times, and then we'll use our fraction thing, control, there's our fraction, and then we have x to the 2n plus 1 power, and then divided by 2n plus 1 factorial. My factorial symbol. Okay. Now, if I expand the control enter, okay, it's giving me all the different values. It's actually giving me all of these different terms for n equals 1 through 5. But I did forget to do something, and maybe you'll notice. Actually, let me show you what happens, something interesting. Let me show you if I just put in, well, no, I'm not going to show you that right now. This actually would just show me all my different terms I got. These would be the values of the factorial with the x, but I forgot to put in the value for x. X is 2 here, so I need to actually do that. So let me get this and put 2, oh my. Let me clear a little bit. What in the world am I doing here? Let's delete that. Let's delete this. Okay, back up. Alright. I'm not sure why I can't get those parentheses to go away. There we go. Alright, let's get this thing again. And now I'm going to put 2 in for x. Okay. So now when I do my decimal approximation, okay, 0.90929. Let's see if that was a good approximation. Good. Okay, what if I only put in 4 decimal places? Would that be enough? So let me change this to 4. 0.90934. So it took, I just happened to guess it on the first try. It took 6 terms from 0 to 5. Notice the first time it only took me 2 terms. This time it took me 6 terms to get 5 decimal place accuracy, to get what sine of 2 was. So 0.90929, and I got, with 6 decimal place accuracy, I got 0.90929. Why did it take more terms this time? Let's take a look at our graph here. And I've got a graph of sine of x. So when I put in just x, notice that's why I got pretty good decimal place. I got a pretty close approximation for sine of 0.2 with just x, because it's really looks close to what the sine graph looks close to the origin. Now, if I add another term to it, which would be minus x cubed over, let me look at my graph going here, minus x cubed divided by 3 factorial, which is 6. Okay, notice now the graph is really close to sine of x from pretty much -1 to 1 in radians here. So I could put in sine of 0.2 and get a really good decimal place accuracy. But if I put in sine of 2, notice right here, it's not going to be very accurate. Okay, if I add another term, so let's add plus x to the 5th divided by 5 factorial, which is 120. Notice the graph now hugs the sine graph farther out. So even sine of 0.2 would be a pretty close approximation, but not exact. So the more terms I add, I'll do one more. The more terms I add, the closer this graph looks to the sine graph. And 7 factorial, I don't know what that is off the top of my head, so I'll use my factorial symbol. So notice how closely almost one complete sine cycle is mimicked very closely now by my power series approximation. The more terms I add, the bigger values of sine I'll be able to approximate accurately with my power function. So notice that sine is an odd function, and all of these are odd polynomials, and the more terms I add, the more curves I add to my polynomial. Actually, the next one looks really cool too, so I'm just going to show you one more, because it curves downward again. So now I'm up to plus x to the 9th divided by 9 factorial. I like this one. I know, I'm a geek. Okay, there we go. So notice we have, this is a 9th degree polynomial, and notice it is, now we have a positive leading coefficient because x to the 9th would be my highest degree term. And you see the curves going on here. Remember that I could have a maximum of 8 curves with an x to the 9th polynomial, but I don't necessarily have to have all 8 curves. But you can see it's going up following the sine graph. So the more terms I add, the more this polynomial starts to look exactly like the sine graph. The reason we use polynomials so frequently in math is because polynomials are immensely versatile, and they can be used to approximate other functions that are more difficult to approximate to do computations. Your calculator can add, subtract, multiply, and divide easily. That's something that you can program a calculator to do. You can't program a calculator to take the ratio of 2 sides of a right triangle that have to be measured. So your calculator has to add, subtract, multiply, and divide polynomials to approximate the sine function. Does the same thing for other what are called transcendental functions, functions that cannot be calculated just by simple arithmetic operations. So I won't spend as much time on cosine because cosine is very similar. If we go to look at our cosine graph, and I didn't actually write down any of these numbers, but hopefully you did fill it in. You can fill in your notes or follow along with the notes. But if I do the cosine graph, what is 1 minus x squared over 2? That's a upside down parabola. What does cosine look like? I actually have the graph on here, I think. Okay, there's the cosine graph. Look what it looks like with just 2 terms added. Add one more term, which would be plus x to the 4th over 4 factorial. Which is 24. Okay, so we have a quartic function now, and the W shape looks very similar. And the more terms we add, the farther out this graph will be approximated by its power series approximation. So these are power series. So what do I want you to remember about the power series? I want you to remember that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Okay, that's the e to the x. Sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, etc. Cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over, I keep writing x's instead of pluses, x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. And to find an approximation in radians for sine or cosine for any of these values, whatever you plug in for x just goes into the powers function, and you can approximate to any degree of accuracy just depending on how many terms you use. So those are the big ideas of power functions. These are something you'll be using in calculus later for those of you who go on to calculus, so I just want you to be familiar with these. The next video then will show you how we use these power functions to find the most amazing equation in mathematics.